Hi, so today I'm going to be doing the CIE AS and A-Level Chemistry October-November 2024 paper 21. Question number 1. Cobalt, rhodium and iridium are metals in the same group, that is group 9, of the periodic table. The shorthand electronic configuration of cobalt is argon 3d7 4s2. Identify what is meant by argon by giving its full electronic configuration. So argon actually has an atomic number of 18, thus it has 18 electrons, and the electronic configuration is as follows: 1s2, 2s2, 2p6, 3s2, 3p6. All the powers add up to 18, and remember, the s subshell can carry 2 electrons max, the p subshell can carry 6 electrons max. The first shell carries 1s subshell, the second shell carries a 2s and a 2p subshell, and the third subshell can actually, the third energy level carries 3s, 3p, and 3d subshells. But in argon, it only fills up to 3p6. The next question says, the lowest energy electrons in cobalt are in the 1s orbital. Draw the shape of a 1s orbital. So as you can see here on the side, I've drawn out a p orbital. It has a dumbbell shape, whereas the s orbital has a circular spherical shape. It says, deduce the number of unpaired electrons in a cobalt atom. So like we saw earlier, it ends in 3d7 4s2. Remember, the 4s subshell fills before the 3d7 subshell. So we have 7 electrons in our d subshell. We first fill up the orbitals singly and then we pair them. So 7 electrons will fill as follows. So go 1 here, 1 here, 1 here, 1 here. That's 5 electrons, and then 1 here, 1 here. Now we have 7 electrons filling the d subshell. Now these two are paired, therefore there are 3 that are unpaired. Okay. Table 1.1 gives some details of the stable naturally occurring isotopes of rhodium and iridium. It asks us to complete table 1.1. Now it's very important to understand how to interpret the isotopes given. So right here on the right hand side, I have given the sort of setup that we use. So here, this would be the symbol for the isotope. Up here is the nucleon number. It's equal to the number of protons and neutrons. And down here is the proton number, which is just the number of protons. And generally, when there is 0 charge, the number of protons is equal to the number of electrons. So here we have for rhodium, it says the number of neutrons is 58. That must mean that the number of protons are going to be 103 minus 58, which gives us 45. So we said that the number of electrons is going to be equal to the number of protons. 45 protons will fill 5 electron shells. Now we know this because rhodium is actually in period 5. So period number actually equals the number of electron shells. Okay? So let's move on to iridium's first isotope. So it says that there's an atomic number of 77. I just realized that we could actually directly just give the proton number 45 from here, my bad. And this one also has an atomic number of 77 because isotopes have the same proton number but different nucleon numbers. The number of neutrons in the first isotope is going to be 191 minus 77, which gives us 114. This one's going to be 193 minus 77, which will give us 116. C. Table 1.2 shows the relative abundances of isotopes in a sample of an alloy containing rhodium and iridium. So an alloy is just a mixture of elements. One at least has to be a metal. So this is our table, and it has asked us to define relative isotopic mass, and this is for 2 marks. So the definition is that it is the mass of an atom of an isotope compared to the mass of the unified atomic mass unit. And this atomic mass unit relative to a carbon-12 atom. So we're basically essentially using a scale in which the carbon-12 atom has a mass of exactly 12 units. So the mass of any other isotope is relative to the mass of a carbon-12 atom. It says here, use table 1.2 to calculate the relative atomic mass of iridium in the alloy. So we have to look at these two right here. It says give your answer to 2 decimal places. Right here on the right hand side, I have given the formula to calculate the relative atomic mass, and that is the sum of the isotopic masses multiplied by their relative abundances over the total abundance. So these are our relative isotopic masses, and these are the relative abundances. The total abundance is the sum of the relative abundances. So 15.18 plus 34.82, which equals 50. Now our AR is going to equal 190.96 times its relative abundance, 15.18, plus 192.96 times its relative abundance, which is 34.82, all over 50. This will give us an answer of 192.35 to 2 decimal places. Question number D. Hydrated rhodium chloride with the following formula catalyzes the conversion of ethene to butene. Both stereoisomers are formed in the reaction. The hydrated rhodium chloride contains 20.5% by mass of water of crystallization. Deduce the integer of the value of X. Now, with water of crystallization calculations, we're always usually comparing the number of moles. So if in this compound 20.5% is water, then RHCl3 is going to be 100 minus 20.5% in the compound. That is equivalent to 79.5%. So what we can do is we can find the molar ratio. So RHCl3 to H2O. Percentage by mass is 79.5 for RHCl3, 20.5 for water. The MR, so the MR of H2O is actually 18, and the MR for RHCl3 is 209.4. Now, if you're wondering where I'm getting these MRs from, I am simply finding the atomic mass from the nucleon number on the periodic table for each atom in the compound and adding them up. So what we need to do to find the number of moles is we're actually going to divide each mass by its MR. So 79.5 divided 209.4 is approximately 0.38, and 20.5 divided 18 is approximately 1.14. If we divide by the smallest number, which is 0.38, we will end up with a 1:3 ratio. Therefore, X must equal 3. Define stereoisomers. So this is a fixed definition. It is molecules with the same molecular formula with different spatial arrangement of atoms. It says explain how the conversion of ethene to butene can be described as an addition reaction. So an addition reaction is when two reactants combine and a single product is formed. It says here, draw two stereoisomers of butene. So but, the prefix, indicates that there are 4 carbon atoms, and the carbon-carbon double bond is in the center. So there are 2 types of stereoisomers for this molecule. There is the cis version, which looks like this, with 1, 2, 3, 4 carbons, and there is the trans version, which looks like this, 1, 2, 3, 4. However, it is very limited, so just beware of the colors. The second question asks us to describe the relative reactivity of the elements chlorine to iodine as oxidizing agents. Now, an oxidizing agent itself is reduced, and if we look at our group 17, we can see that down the group, the shielding increases. As a result, a positive nucleus is actually shielded more and more as you go down the group. That is what attracts the electrons. Now, reduction is the gain of electrons. So the more shielded the nucleus is, the less able it is to gain electrons as readily. Therefore, the oxidizing strength decreases as you go down the group from chlorine to iodine. State what is observed when chlorine reacts with hydrogen. So when chlorine reacts with hydrogen, HCl will be formed, and that once green color that chlorine has will disappear. Explain why the thermal stability of the hydrogen halides decreases down the group. So as you go down the group, the HX bond, where the X is the halogen atom, the strength of this bond actually decreases, and therefore it is more easier to break the hydrogen iodide bond than it is to break the HCl bond. So what we can say for this is that the H halogen covalent bond strength decreases down the group, so less heat energy needed to break the bond as you go down. B. The halogenoalkane CH3CH2Cl forms when chlorine reacts with C2H6 via a free radical substitution mechanism. Define free radical. So a free radical is a species with one or more unpaired electrons. So for example here, when we are doing free radical substitution and we have a chlorine molecule, it is basically 2 Cl atoms bonded to each other. They can be broken down to form 2 individual chlorine radicals, which will have a free electron each. This condition, the condition needed for this to take place is UV light, because for chlorine to react with C2H6, the chlorine molecule must be broken down into free radicals first. Propagation steps basically involve a radical combining with a non-radical. So firstly, the chlorine-fluorine free radical is going to react with the C2H6. HCl will be produced. 1 H from the C2H6 is going to be removed to produce this HCl. So we'll end up with C2H5, and now we have formed a C2H5 radical. This C2H5 radical reacts with a chlorine molecule to then form C2H5Cl and a free chlorine radical. So I forgot to mention this as well, but in a propagation, we also produce a radical and a non-radical. So CHCl3 is another halogenoalkane. It forms when propanone reacts with NaClO. NaClO is made from chlorine in a disproportionation reaction. Identify a reagent and conditions that can be used to convert chlorine to NaClO. So we actually use NaOH, and it must be cold for the reaction to take place. It says here, define disproportionation. Disproportionation is a reaction where a species is both oxidized and reduced simultaneously. So for example, in the reaction where chlorine reacts with sodium hydroxide, this is the equation or the reaction that takes place. NaClO plus H2O. And you can see that chlorine is actually oxidized and reduced. We can determine this by looking at the oxidation state changes. So in chlorine, it's a element, so it has an oxidation state of 0. In sodium chloride, it has an oxidation state of -1, so it's gained an electron, so it's been reduced. And in sodium chlorate, it actually has an oxidation state of +1, so it must have been oxidized. Here it says, write numbers in the boxes to balance the equation showing the reaction of propanone with NaClO. So if we consider this compound to have 1 mole, we can see here that there are actually 3 Cl's here, but only 1 here. So we're going to add 3 at the start here. And now we actually have 4 oxygens on this side, but only 3 oxygens on this side. Well, we have to multiply this by 2. And this remains as 1. And therefore we have a balanced equation. So here it says aqueous AgNO3, which is silver nitrate dissolved in ethanol, reacts with an aqueous solution of CHCl3. State what is observed and explain your answer. So what the ethanol is going to do is it's actually going to release chloride ions from CHCl3. These chloride ions can react with Ag plus ions from the silver nitrate to form AgCl. AgCl is a white precipitate. Question number 3. The group 14 elements show a change from non-metallic to metallic character down the group. Table 3.1 shows some properties of 2 of the group 14 elements, carbon and tin. In their standard states, the table is incomplete. Complete table 3.1. So it's asking for the electrical conductivity of carbon, or to be specific, graphite. Now, right here is the structure of graphite, and if you look closely, each carbon atom is bonded to 3 other carbons, but there are 4 outer electrons in the carbon atom. Therefore, there are delocalized electrons which can flow to form a current. Thus, they actually have good electrical conductivity. The type of bonding in graphite is covalent, because it's between 2 nonmetals, carbon and carbon, per bond, of course. It's asking for the type of structure of tin. So tin is a metal, and it is giant for that reason. Here is the structure of tin. It is a giant metallic structure consisting of a lattice of metal ions in a sea of delocalized electrons. It's asked us to identify the lattice structure shown by graphite. So it's giant because it consists of many, many, many atoms, and it's molecular because it consists of covalent bonds only. Explain why tin has a good electrical conductivity. So because tin has delocalized electrons, this means they are free to move, and the flow or the movement of electrons forms a current. Carbon is found in inorganic compounds such as carbonates. Write an equation for the reaction of magnesium carbonate with dilute HCl. So an acid. So whenever a carbonate reacts with an acid, we produce a salt, carbon dioxide, and water. So the reaction for this is going to be MgCO3 plus 2HCl to give MgCl2 plus CO2 plus H2O. Here it says describe the thermal stability of carbonates down group 2. Now the thermal stability down group 2 increases. This is because as you go down the group, the shielding increases, and so they actually polarize CO3 to minus ions a lot less. This makes it harder to break it down into a metal oxide and carbon dioxide. It says here, ammonium carbonate undergoes an acid-base reaction with sodium hydroxide. Explain the statement. So this is actually the formula for ammonium carbonate. It consists of NH4 plus ions. NH4 plus ions are capable of donating H plus ions. So NH4 plus donates hydrogen ions. Therefore, it acts as an acid, and the OH minus ions accept these hydrogen ions, acting as a base. Here it says, figure 3.1 shows a sketch of some of the ionization energies of silicone. Complete the graph in figure 3.1 to show the third to the sixth ionization energy. So the ionization energy is just going to increase. That is because the ionization energy is the energy needed to remove electrons from the outer shell. As you remove the first electron, the atom is going to become an ion, a positive ion, and there will be strong attractions between the nucleus and the outer electrons. However, silicone is in group 14, which means it has 4 outer electrons. So once you've removed the 4th electron, you're actually going to have to remove electrons from a closer shell. So this will mean that a lot more energy will need to be applied after the 4th ionization energy. So this is just going to be an approximation. So what we're going to do is we're going to increase it, but we're going to make sure that there's a large jump between the 5th and the 6th. Perhaps make the jump a little bit bigger. Yep, that looks about right. Construct an equation to represent the second ionization energy of silicone. So if it's a second ionization energy, then it must already have a +1 charge. It must be in the gaseous state to form Si2+ in the gaseous state plus an electron. Part D. Figure 3.2 shows the boiling points of the simplest hydrides of the group's 14 elements, C to Pb. Explain the trend in the boiling points shown in figure 3.2. So as you can see, as you go down the group, the boiling point increases. This is because as you go down the group, the atomic number is going to increase, and so will the number of electrons. So a greater number of electrons What this means is there is going to be greater London forces. Thus, more energy is needed to overcome these forces. And so the boiling point increases down the group. Down here it says deduce the shape of a molecule of SiH form. So silicone has 4 outer electrons. There are 4 hydrogens. So there is a total of 8 electrons in the outer shell. Divide this by 2 to find the number of electron pairs. There are 4 electron pairs, and we're bonding silicone to 4 hydrogen atoms. So there must be 4 bonding pairs. Therefore, we get the following shape. And this is what we call a tetrahedral shape. Silicone readily reacts with elements of high electronegativity. Write an equation for the formation of SiCl4 from its constituent elements. So SiCl4, as you can see, consists of 2 elements, silicone and chlorine, to form SiCl4. Because there are 4 chlorines on the right hand side, we must multiply the left hand side chlorine molecules by 2 to balance the equation. Describe what is observed when a small sample of CiCl4 is added to water. So I've written the equation on the right hand side, and we form silicon dioxide and HCl. Now it is in aqueous solution, but some HCl gas may be produced. So we may see some effervescence. And if you want to be more specific, you might see some white fumes because HCl gas produces white fumes. Here it says silicon dioxide is a white solid. It melts at above 1700 degrees Celsius. SiCl4 is a colorless liquid at room temperature. So if it's a liquid at room temperature, while silicon dioxide is a solid, and it's a solid way beyond 1700 degrees Celsius, thus that must mean that silicon dioxide has a greater melting point than CiCl4. And the difference in this is because you need to recognize that silicon dioxide is a giant covalent structure, while SiCl4 is simple molecular. There are some... Now, what this means is the IMF forces in SiCl4 must be a lot weaker than the bonds in SiO2. Now be careful because it's the bonds in SiO2, because the many covalent bonds in SiO2 is what makes its melting point so high. However, in SiCl4, it's the intermolecular forces that play the role. Tin forms an atmospheric oxide, tin dioxide. Suggest the formula of the tin compound that forms when tin oxide reacts with sulfuric acid in an acid-base reaction. In an acid-base reaction, a salt will be produced. So this will consist of a metal sulfate. In this case, because we're using sulfuric acid, so we should end up with tin sulfate. Now, first we need to determine the oxidation states. So the SO4 2- ion, the sulfate ion, has a charge of 2-, and in tin oxide, oxygen has an... Wait, let me just move this down here. Oxygen has an oxidation state of -2, but since there are two of them, it has an overall oxidation state of -4. So to make the overall charge equal to 0, the tin has to have an oxidation state of +4. Now, the metal sulfate has a charge of 0, so we will require 2 sulfates per tin. Because now we have +4, and then we have 2 times -2, which equals -4. +4 minus 4 equals 0. So the answer here is tin sulfate. Question 4. Propanone is an important organic reagent. Figure 4.1 shows some reactions of propanone and its derivatives. Reaction 1, right here, is a nucleophilic addition reaction. Complete figure 4.2 to show the mechanism for the formation of A from propanone. Include charges, dipoles, lone pairs of electrons, and curly arrows where appropriate. So the first thing I'm going to do is I'm going to determine the dipoles. The carbon atom here is less electronegative, while the oxygen atom is more electronegative, so it takes the delta negative. With nucleophilic addition reactions, the CO bond is always broken and the allyl goes from the bond to the oxygen atom. And here the CN, so the nucleophile, is attracted to the carbon. The intermediate that we will get is, since the bond has been broken, we're going to have a lone pair on the electron. It's going to be negative now that it's received the bond, essentially, because the bond is electron dense, of course. We'll have our H3C here, CH3 here, and now we'll actually have a CN bond. Now, usually CN is followed by dilute acid, so there'll be H+ ions, and the lone pair on the oxygen atom attracts that hydrogen ion, and we end up with a hydroxyl group. Explain why A does not show optical isomerism. Whenever something doesn't show optical isomerism, it must mean that there is no chiral center. So the central C atom is not bonded to 4 different groups of atoms. And if we take a look, this is our central carbon. There are actually 2 methyl groups, therefore 2 same groups. It says suggest the reagents and conditions for reaction 2. And if we go back here to reaction 2, we're going from a nitrile to a carboxylic acid. For this, we need a acid, so we can either write down sulfuric acid, for example, or hydrochloric acid. Part C, reaction 3, is a reduction reaction. Construct an equation to represent reaction 3. Use this to represent 1 atom of hydrogen from the reducing agent. So if we go back to reaction 3 right here, we're going from a propanone to a 1, 2, 3 propan-2-ol. So this is most definitely a reduction reaction. Now we need to determine how many hydrogen atoms we need. So we will start off with our CH3, then we'll have a set number of hydrogen atoms, and we will produce CH3, CH, OH, CH3, and that's just the structural formula for propan-2-ol. So let's look at so first of all, we're going to break this double bond. This is going to be an OH, and carbon atoms bond to 4 other atoms. So we'll get another H on this side. Therefore, we've added on 2 H's, so we need 2 H atoms from the reducing agent. Now it asks us to name C, which we already have done. It is propan-2-ol. State what is observed in reaction 4. So if we take a look at reaction 4, we've taken propanone and we've added 2,4-DNPH. Now, 2,4-DNPH is used to test for the presence of the carbonyl group, the C double bond O group. And since it is present, we will get a positive result and we will end up with an orange precipitate. The mark scheme also accepts red and yellow. Explain why Fehling's reagent does not react with propanone. Now, Fehling's solution is an oxidizing agent, but it cannot oxidize ketones. Therefore, no reaction. And this is because ketones aren't easily oxidized. And the last part, part F, compounds A, B, and C can be distinguished using infrared spectroscopy. Figure 4.3 shows the infrared spectrum of one of these compounds. This is the infrared spectrum right here, and these are the absorption ranges for each functional group. And I here asks us explain why the absorptions at 2850 to 2950 are not useful to help to determine which of the compounds produce the infrared spectrum. So if we look at 2850 to 2950, that represents the CH bond. However, if we take a look, all three compounds will consist of CH bonds. Therefore, it's not useful because it will be present in all of them regardless. It says identify which of the compounds produces the infrared spectrum in figure 4.3, determine the compound, and provide an explanation. So the way we're going to differentiate between each is to look at our differences. They all have an OH group, so we all expect for them to have a peak at around 3,200 to 3,600, which is around about this peak right here. However, A has a CN group, so this group right here, so 2,000 to 200, 2,200 to 2,250, 2,000, so 2,300 is a roundabout here. So you can say this peak is probably the C triple N bond peak. However, we need to double check. So B has a COOH group, so the hydroxyl group for carboxylic acids has its own peak at 2,500 to 3,000. However, I don't see a peak in this range, so it's definitely not B. Now C will only have an alcohol group and no other peaks elsewhere, but like we said earlier, we determined the CN functional group peak right here, so this must be the infrared spectra for compound A. So we state that it's compound A and there is an absorption at 2,200 to 2,250 centimeters, which indicates that C triple bond N group.